So I hope this example really brings in abstract that why and how pseudo-random number generators are different than true random number generators, and two, why once we switch the and utilize the pseudo-random number generators in the one-time path, it would not be computationally secure. It would be only computationally secure, and we would move away that notation of unconditionally secure. So that we talk about stream ciphers, we would come back. We would have different design for the stream ciphers, but I think it's the best time to start to talk about block ciphers. First of all, in abstract. This is going to be very important for your understanding of how the block ciphers would work in the first place. So the first thing first we have is that we would have some message space and ciphertext space that we can represent them in different bits. So if you want to see them in the integer perspective, we can have numbers from 0 to 2 to the n minus 1. These are like the many different number integers that we can represent here. And so we say that a key is a set of permutation from this space to the other space. So remember that we have a function that it takes message to a ciphertext. Now you're talking about a function that a domain of this function is the same as the range of this function, right? So it maps from domain to the domain itself. It looks like that we have the same thing. But what does that mean that the key is a permutation, a set of permutations? So this is how we would represent all the elements in the message space if we want to see them, index them from 0 to n minus 1, and correspondingly the ciphertext space. And when you choose a key from a key space, this particular key would map the elements from the message space to the cipher space with a different pattern. For example, the message M1, when you choose this particular key, M1 would get mapped to C3, and then M3 would map to C0, and so on and so forth. And this is like 1 to 1 and onto. So therefore, there is no ambiguity. When you want to go back from cipher space, this key would map C0 to M3, and so on and so forth. So that's how I want you to guys see how the encryption and decryption algorithm works. So remember that M0 is actually a representation of n bits. So we have 0, 0, 0. So together we have n bits, so that we would show them as, we would symbolically show them as M0. And so on and so forth. We can have the same encoding for the ciphertext space. So we would have a bunch of zeros and, ending with 1, 1. And that would be n-bit representation for the C3. So that is being clear. And now there's something that is very interesting, and that is the number of the permutations that we have for the set key K. So now we are interested to understand how big this, the set of capital K, the entire keys are. And it turns out that we are computing the size of this set K. And it turns out that this is 2n factorial, and this is a little bit surprising. So the way that you can think about the computation, so for the first key that you want to assign, suppose that we want to choose K0, then we have 2 to the n different permutations that we can make. And then once we set, one permutation, the way that the key 0 or key 1 would set this, different mappings, then for the second one, it would have 2n minus 1, because we already have one of those permutations, and so on and so forth. So if you multiply all these numbers, you get this huge number 2n factorial, right? So Remember something that the numbers are getting large. Remember that from a set of n elements, a set with n elements would have n factorial different permutations, right? This is a number that we knew from before, but now we have 2 to the n different elements. So once we would do the math, we would end up with a key size to be 2n factorial. So what does that mean? That means that my key size k, if I want to represent the elements over here, I would like to represent them with key 0. Actually, let me do a better work. So let's say I want to show them with the permutation 0, permutation 1, permutation 2, permutation 3, and all the way to permutation 2n factorial. This would be a set of all these elements. When, for example, the permutation k would be m0 mapped to I don't know, c3. Let's say m2 would map to c I don't know, 300. M3 would map to C0, right? And so on and so forth, right? We would go all the way down to M2 n minus 1 to maybe C, I don't know, 2n minus 10, like something like that. And the rest of the, messages and ciphertext spaces. So every key is actually a permutation. Every permutation would define exactly how do we map every single message to corresponding ciphertext. And once we have one way, the other way around would be also easy to do the computation. So we would start to do indexing these elements. So if you look at these elements over here, instead of just saying key equals to this thing, we would instead use indexes. For example, this would be key 0, key 1, key is equal to 2, 3, all the way to k, and then all the way to, whatever that it takes to represent those numbers. So when we are saying that the key equals to k, we are just using the kth index, and then the kth index represents itself is a permutation that defines what elements would map to, from message space, would map to which elements in the ciphertext space. So this is a true definition of block ciphers. So as we said, they are one mapping, and this is how we would specifically define our key space. And then we would also define, we saw how to define one of the keys properly, but just because we don't want to write down those old things, so we would try to index them. And when we said that key equals to k, it means that we are talking about permutation k. So remember that. That is how we want to see these things. Okay, now that we understand the number of the permutations that we have and the message space and the cipher space, then let's talk about two different concepts. We would have something called ideal block ciphers, and also we have something that it calls practical block ciphers. So it sounds weird, right? So the moment we haven't even started to talk about block ciphers and we just get to know ideal and something that it called practical, something is wrong. And the answer is yes. So ideal block cipher, we start to call it a true random permutation. True random permutation, it means that the set capital K is a set of all possible permutation from message space to the ciphertext space, right? And so unfortunately, when you want to represent all the elements, the index all the elements in this set, we said that the size of the key set is 2 to the n factorial. They have that many different indexes. And that 2n factorial with the Starling, approximation, that equals to be 2 to the power n minus 1.4 times 2 to the n. And we know that in average, we need log of this many, log of this integer. This is the maximum index that we would have. And in average, we know that we need log of this value to many bits to represent this value. So if we take a log of base 2 of this value, the maximum value that index that we have, it happened to be n minus 1.4 times 2 to the n number of bits we need to represent this key size, right? So this seems like that indexing, the indexing is this different indexes that we've defined over here. So this value goes to happen to be very large, and it looks like that when we want to represent those indexes, we need this many bits. This maybe is something that doesn't seem to be high, but let's just plug in some numbers. For example, AES algorithm, we know that the block cipher n is 128. So when we plug 128 over here, and then you would find that, well, in order to present a key in a key space, this key is an integer, and we have so many integers that we need almost terabytes of bits to represent this key k. That, this key is just an index of, the key that we have. And imagine how many indexes that we have, that we need terabytes of data to present just the index of the key. And therefore, all of a sudden, we would find out that, well, the block cipher, there is a problem, and the key size happened to grow very fast, and it is just huge. So if, for example, with AES, you want to encrypt 1 megabyte, it doesn't make sense to transfer, I don't know, terabyte of key just to encrypt 1 megabyte of file, and that does not make any sense. And then people start to wonder, so what can we do about it? So there we start to work on practical block ciphers. And in order to make this thing practical, we have to do some sacrification. So we sacrifice the key size, and instead of working on the entire key size, we would start to use a subset. So now the keys space is just a subset. Remember, here is all, but now we start with the subset of all permutations from message space to cipher space, right? So it does not cover the entire set of keys, and it's just a small subset of them. And roughly, the size of the key is normally 64-bit or 128-bit or 256 bits. We need to represent the key, right? So compare 256 bits with this many bits, then you will understand that why there is a huge gap between them. Just like, true random number generator and pseudo random number generator, that you see that we miss half of them. But it seems like now we are missing a lot more. Instead of, having terabytes of bits to represent the keys, now we just use, I don't know, 256 bits to represent the key. So it really looked like that we are missing a lot. But this is the point, that the key size, even though it loses a lot of keys, but it still look like a set of all permutation. And how it looks like to be a set of all permutation, this is really a design of this block cipher. And generally speaking, design of a block cipher is equivalent to some art. How can you achieve the security when you reduce the key size from some terabytes down to some few bits? That would just become an art, the way that somebody would get to design it, and still can prove that some block cipher would remain secure. So I really hope that you take this piece of advice here, that when somebody says that I design a block cipher, or a block cipher is out there and is perfectly secure, and immediately you would say you don't buy this, because you know that in order for some block cipher to be unconditionally secure, then that means that you should have a set of all possible keys, right? And by design, the block ciphers that we use today, we call them pseudo-random permutations, because they don't have all possible keys. And the moment that you shrink the size of the key, then we know that we do not have unconditionally secure block cipher, and we would downgrade to computational version. So it looked like that in the year 2023, writing a for loop to iterate over all possible keys with 256 bits is a still challenging task to do. So those algorithms, such as AES, that use 256 bit for key, would still remain considered to be secure, because with the computational power that we have now, unfortunately or fortunately, we cannot break AES, and therefore we are still in a safe time, and until some time that we have enough processors or computational power so that we can easily beat this 256 bit, then that would be the time for us to move to some higher bits and keep the thing secure. So I really hope that this draw the line, and you can imagine that whatever that you are using now, it is the computational version, and this is not perfectly secure. But one of the questions that you can ask yourself is that, can we show that the ideal block ciphers are basically perfectly secure? Can we answer that question? So let's try. So the question that we want to answer is, we want to say, is the ideal block cipher secure? So is the ideal block cipher perfectly secure? So this is the question that we want to answer. In order to answer this question, we know that from the equation that we have is that we have to show that if something is perfectly secure, it has to have this semantic, that probability of message to be M0 given that the ciphertext is 0 is, according to the Bayes theorem, we have probability of C equals to C0 given M equals to M0, probability of M equals to M0, right? And then here we have probability of C equals to C0. All right. So, okay. So now that we have perfectly secure or ideal block cipher, so we know that whenever you choose a key, this key comes from a set of all permutation, right? So it's a true permutation. So key that we choose is chosen from a true random permutation, right? So that is the definition of ideal block cipher. So if that is the case, then we can rewrite this equation as following. So how do I compute this first probability? This thing seems to be a bit challenging, right? So what it says, let's look at this a bit more carefully. It says that I choose M to be M0. What is the probability of this, keys that are out there, so that it map it exactly to C0? So in order to compute this probability, let's use a trick. So imagine that I want to compute and see how many different keys are there, with what probability this M0 would map to C0. So in order to solve this problem, what I can say is that suppose I fix this. I say that from M0, I draw a line to C0, and that permutation is fixed. So M0 would always map to C0 and vice versa. So how many other keys that I have left? So I can do that 2n minus 1 factorial, right? If I fix that one. And we are talking about the probability. So what are the all different combination of keys? 2n factorial. Okay. So again, one more time, why did it become 2n minus 1 factorial? Because I fixed the mapping between M0 to C1. And this is as many permutation that I can have. And of course, multiply to again PM equals to M0 that I have. And then the other one is that what is the probability of C to be C0? So I have 2 to the n different C's. And then supposing that they are uniformly random, they are chosen. So the probability of C to be C0 is just 2 to the n, right? Because I have 2 to the n different C's. So when you do the math, so what we would get over here is, if you do simplify here, we would get 2 to the n, we would get 2 to the n times 2 to the n minus 1 factorial over 2n factorial times probability of m equals to m0, right? So this seems like that this is exactly going to be 2n, right? So we can rewrite this one to be 2n factorial over 2n factorial. And this is time p of m equals to m0. This gets canceled. And we end up by probability of m to be m0, right? So we exactly show what happened here. So again, assuming that the key is coming from a true random permutation set, then we would be able to show this equality, and therefore our adversary would not gain any information by observing this C0. So whatever this computation is showing us is that we get back to the distribution of the message space, which we show from the first base. So I can say that I can have perfect secrecy when K is chosen from a set of all permutation, right? So therefore, as long as the key is chosen from the set of all permutation, then we can say, whatever block cipher that is, that we call it ideal block cipher. We don't care so far about the construction, how it works. As long as it uses a set of entire keys, then it can be unconditionally secure or perfectly secure. But the problem now that we have is that the practical block ciphers that we use on the market, we know that the key is definitely not chosen from a set of all possible keys. And therefore, no matter how we construct the practical block ciphers, they can never be unconditionally secure. So that is what we get. Just a second, let me close the window. So I hope now it is really easy for you guys to understand how and why the ideal block ciphers are not secure anymore. Just once we do the math, we knew that when logically, when the key is not chosen from the set of all computation, all possible keys, then the brute force attack would become easier, because we basically roll out a lot of different possibilities for key, and therefore that for loop that goes through all possible keys would become a bit more practical. And the moment that we would get rid of that set of all random permutation, and we go back to the set of look like how do we call it, a subset of all permutations, then mathematically we show that it cannot be perfectly secure no matter what we do. So this is a stronger proof, and therefore, again, one more time, that if somebody suggests on the market that there is a practical and efficient block cipher that achieves perfect secrecy, I think now you would deeply understand the issue and you will not buy that idea, right? Because it is not possible to achieve it. All right. So I think enough a story of understanding what is things are going on. Unfortunately, we don't have much time left, but I think we can start with some basics of the DES algorithm. So the DES algorithm, we won't go so much into the details because this algorithm is not used anymore. But just to understand a little bit of basics of this algorithm is algorithm that would take a key that is 56 bits and it takes a message that is 64 bits and it would map it to the ciphertext space that is 64 bits. So I can say M equals to C equals to 0 and 1s of 64, right? 64. So this is the key. This is M. This is a ciphertext. So the other way that we can represent this one, we can say that DES of given KK, when the key is given, it would map a set from 0 1s of 64 bits to the ciphertext space that is also happen to be 64 bits, right? So the first thing that our algorithm would do is what we call it a key expand function. So the key expand, we are given 64 bits for this algorithm to do this encryption, but you will see in the construction very soon that that is not just enough. So there is a pseudo random number generator, something like that, that we call it just like key expand here in the construction, that would take this key K and construct 16 different keys, and every key is for these 8 bits. So it looked like that we are talking about an algorithm that takes 56 bits, and in a polynomially timed algorithm, he would map them to 16 keys, and each is 48 bits, right? 48 bits. And if you look at these numbers, so it is going to be basically 13 times longer than original key, than key that we gave to this algorithm in the first place, right? So that is how we call it a pseudo random number generator, and over here is just like getting these keys, expanding them to 16 different keys, and this algorithm is a sort of a rounded algorithm that we have 16 different rounds, and every key is going to be used in a corresponding round, and every round we would do some computation until we would get to the last part where we would basically compute the ciphertext. This is how this every round would look like. So every round function, it is like I drew this one in this box. So this is fki and x. So the ki is one of these round keys depending on the round number. The x would go in, so we only would basically work with a half of a message. So our message is 64 bits. We cut it into 2 parts, left and right, and depending on the round, we would just take one of those parts, and then what this function would do is the bits would come in. We know that the key that we are using, the round key, is 48 bits. So the function try to XOR this 48 bits with our message, with our input x. But since the x is 32 bits, it doesn't really make sense to XOR it with the 48 bits. So what algorithm would do is some expansion P boxes that would take this 32 bits and it would expand those bits to 48 bits to become equal to this round key that we have. Once we have expand them, we can XOR them together. And then once we XOR them, we kind of need to convert that 48 bits back to 32 bits. So that's where the algorithm would use the notation of S boxes, so substitution boxes. So we will talk about them in details later, but just like I want you guys to see the overview. So this S boxes would take these 48 bits and convert them back to 32 bits. And then we would apply some permutation box, and then we would output the 32. So in short, you would get the input, the round key, and the input, which is 32-bit, expand it to 48 bits, XOR it with key, and then shrink it back to 32 bits, and then we'll do one more permutation, and then give it output as a 32-bit again. So this is the algorithm. That is how it look like. So the algorithm would take this X, and if I want to show it in mathematical formulas, so the first thing we get is that we get the X, we expand it with E. E here is not encryption. E stands for expand box. So let me just draw a line here. And then we can then, once we get this, after expanding X, we get 48 bits. We would be able to XOR it with round key. And then we pass this one to S boxes over here, that this S boxes would return this, shrink this 48 bits into 32 bits. And then we do, one more permutation. And then once we are done with that, we can give it as an output. So as a reference, the key is 48 bits and the X is 32 bits. So this is the key I, this is X, and then we always output some Y that is also happen to be 32 bits. And we want to do this computation for every round. So as we said, for the case of DES, we have 16 rounds, and we would have to do this computation for that all 16 rounds. Let me see how much time do we have. And okay, maybe I can just stop here because I don't want to go a little bit forward and then we have to stop it. So let's continue on DES for next week. So we would just stop over here. Do we have any questions? If there is no question, the class is dismissed, and we'll see you guys next week. 48 plus 16 is 56. Are you talking about the key over here? No. This is multiply. 16 multiply 48.